evolvr is my first excursion into machine learning and evolutionary algorithms. An evolutionary algorithm leverages natural selection to solve computational problems in a strikingly similar way to how biological evolution occurs in nature. So in an evolutionary algorithm, you have a data structure with a modular sequence of instructions, and this sequence of instructions can be reordered, mutated, and hybridized just like a genetic code. So once you have this data structure, you'll copy it a bunch of times into the memory, and then you'll one by one score each potential solution based on how well it meets an objective criteria, and this will be its fitness score. So in this specific example, organisms or potential solutions start right about here, and then they execute this list of instructions. The list of instructions is just an array of integers 0 through 3, representing left, up, right, and down respectively. After they execute that list of instructions, then they're measured for fitness based on their distance from this goal point right here. So the closer they are to this, the higher their fitness score will be. So once you've scored the fitness of each potential solution, then you'll start to kill off solutions statistically based on how fit they are. So an organism or potential solution with a really low fitness score will have a really high chance of being killed, and a solution with a high fitness score will have a high chance of surviving. So then from there, you take that surviving population of solutions and you interbreed them with one another while injecting random mutations into the results. So there's 3 different types of mutations that can occur when 2 organisms interbreed in this example. Each has about a 5% chance of occurring. You can randomly insert an instruction into this step list. You can randomly delete an instruction from the step list, or you could shuffle the entire step list. So from there, you keep going in these iterations of scoring the fitness of every organism, killing off the weak solutions, and interbreeding the surviving population. And every successive iteration, the solutions get more and more optimized. So in this specific example, before we execute it, there's a few things we can observe about what's going to happen. First of all, it's worth noting that this view right here of the map will show the location of the organism that has the highest fitness score. Starting out, there's only 10 organisms, but this will quickly rise to a soft cap of about 2,000. So it's important to realize that this organism location right here is somewhat of an outlier. So starting out, as I mentioned, organisms start right about here and then execute their step list to get their fitness score. So what we'll see is that the population will reach a temporary point of stability right about here. These hashtags represent barriers that can't be crossed. So the temporary stability point right here occurs because in order to get closer to this goal point, an organism will have to go up around this barrier, and once it starts moving upward, it actually loses fitness because it increases the distance from itself to this goal point. So it'll take a while to go over this hurdle because it has to overcome negative fitness to eventually get the long-term gains of positive fitness. So you'll see it kind of stick here, but every once in a while you'll see it peak over this and then kind of get reintegrated back into the population. Remember, this is the fittest organism and it is an outlier to the entire population, so when it finally makes it over here, it will get reintegrated back into the population, sort of like regression to the mean. But that will start sending ripples through the entire population, and the population will slowly kind of migrate up over this barrier and start descending on this goal point. Once it gets sufficiently close to the goal point, about right here, the organisms are so fit that they start becoming really difficult to kill. So you'll see the population size go from the soft cap of 2,000 to the hard limit of about 10,000. But eventually the fittest organism will make it to this goal point right here, which will give it a perfect fitness score of 0 and basically make it impossible to kill. And then from there, we have a population sample right here of just a randomly selected sample of 5 organisms in the population. And once the fittest organism makes it to this goal point right here, you can observe what happens to the fitness scores of the rest of the population. At first they're mixed, but as time goes by, they homogenize around a single point of perfect fitness. So you'll see initially mixed fitness scores, and then they'll transition to being all perfect fitness scores as the instruction sequence for the fittest organism propagates throughout the entire population. So let's go ahead and run this real quick. So there's the point of stability right there up against the barricade, and then it just peaks over, and it's doing pretty good this time around. You'll see the population size is now up to 10,000, and then if you look at the fitness scores on the population sample, they'll slowly be converging onto perfect fitness here real soon. Yep, there we go. So, thanks for listening. That's evolvr.